All right, so today we're going to be discussing the dot product. Somebody might have asked, hey, Jay, we can add vectors. Yep, we can subtract vectors. You betcha. Can you multiply them? Kind of. There's two ways to multiply them. Two different kinds of multiplications. One of which is the dot product. One of which is the cross product. They're different. They do different things. And they will actually tell us, different, obviously, they're different tools. This one's also referred to sometimes as a scalar product, because when you're finished with this one, when you're done, you're going to get a number, 5, 10, -3, whatever it happens to be. And that scalar product is a scalar, and we're going to be using it to tell us several different things, and we're going to see how that plays out in a few minutes. Okay. It can be used for a variety of reasons. The other multiplication one, the cross product, which is going to be talked about 9.4, will actually, two vectors multiplied together will give you a different vector, but it's different, and there's reasons for why we do the different ones. Okay, so suffice to say, if you take A dot B like this, right? Whoa, is that real multiplication? No, it's always going to be, when you write this way, it's called the dot product. Okay, now, what is that going to tell you? Before I tell you that, what I prefer to tell you is this. Sometimes it'd be kind of nice to know, hey, here's a vector A, cool. Here's a vector B, sweet. Can you find the angle between them, Jay? I don't know, but I bet that'd be kind of a neat thing to do. I mean, for instance, it'd be really cool, for instance, if I could find a way to show if they're perpendicular or not, or orthogonal, as it were. And you're right, that would be a neat thing to be able to do. In the case of, you talked about work back in the day. Remember pushing, when the kids were little, we had this stroller, had like these tiny short handles on it, and I'm not real tall, but I'm 6'3", but I'm not like a monster or anything, of course. But it was ridiculous for me to push this stroller, and I don't know why the kid's just floating, but whatever. Anyway, there it is. Anyway, why I went into math. Reason number 7 million why I went into math. Let me draw me with some hair. Back in the day when I had hair, awesome. Anyway, what else? So I'm pushing this thing, and I was not a happy camper, because as I'm pushing it, all right, all of my force basically is forcing it down into the ground, because I'm pushing down along my arms like so. And most of it's pushing downwards, and very little of it's pushing this way. And then, of course, it's only this part here that actually makes the thing move, which, yeah. And so if you recall, work is equal to force times the distance, right, back in the day. And you're like, oh, yeah, work is force times the distance. That makes a lot of sense. Right on. And you're like, well, cool. We're moving this along the ground and so forth. But what part of the force? Well, it's the part that is in the direction. So when I normally teach this in physics, I write force times the displacement, the distance you moved it. But I usually write force sub x, because it's the force that's in the direction of the movement that's actually doing the work. That makes sense? So that's the part that actually matters, is how much is in that direction. And of course, it's going to be this piece right here. And you're like, oh, sweet. And you're like, so yeah, okay, well, that's nice. Now what? Well, what do I do about that? Well, of course, there's going to be some cosine involved here. You're like, well, what do you mean cosine? Well, here is x is going to be this distance from hither to yon. Okay. And then my force, if you drag this is my force vector right here. It's, there's an angle right here, this little theta right there. And so this f sub x business is going to be equal to the force times the cosine of that angle. Nice. And so, you've done this in physics. It's nothing new. There's nothing exciting about that at all. And you're like, well, what if my x was actually going up a hill? Well, then part of your work's going to be against gravity, and part of it's going to be, in the horizontal direction. And then, of course, you might be pushing your kid in a stroller like so, but you're like, oh, but it's not like perfectly pushing it into the hill. Maybe you are, maybe you aren't, whatever. So there's going to be different vectors here. And so it's going to be kind of a mess. And so, what a nuisance. I don't want to do all that work. Yeah, I don't either. And so what's going to be kind of interesting is this idea that this angle between them is kind of a big deal. Okay, whether you're pushing here in this case where the ground is flat and your angle is just, you're not pushing horizontal with the thing, horizontal with the movement. I mean, it would have been cool. And I actually did threaten to do this. My wife got really angry with me, as you can maybe imagine. I said I could just make the handles taller so the guy can just push them like so. She was not pleased with that idea. She said, that looks stupid. I'm like, you're not doing that. I'm like, but it would be easy. She's like, no. All right, fine, whatever. So it would have made me happier to do that, but whatever. So, but again, in that case, all of my force would have been horizontal, and I wouldn't have to do any of this cosine business. I could have. Cosine of 0 is 1, so that would have been easy to do, but I didn't need to. So this angle would have been kind of neat to know. So that cosine of the angle between them turns out to be defined to be A dot B, whatever that is, over the magnitude of A times the magnitude of B. And you're like, okay, I guess, cool, maybe. And yeah, no, it is. This is exciting, man. This is exciting. And you're like, oh, okay, I'll take your word for it, I guess. So then, wait, so you could rewrite this a couple of different ways, Jay. I could. So A dot B could be written as, now wait for it, A magnitude. Now I'm going to write it like this, and I'm going to change it up in just a second. And then you're like, wait, I feel like this looks an awful lot like this. Well, let me back the train up a little bit. There you go. Nice. Oh, what? In other words, if you were to let B, let's just say that B is equal to my force vector. Nice. And A is equal to my displacement vector, then what I have right here is really, then I'm just going to have, I'm going to change it around because it looks stupid the other way. Sorry, my bad. I don't care. I'm doing it anyways. I'm going with it, friend. Then this thing right here is actually work. And as you recall, back in physics, work is a certain, it is amount of stuff done. It has nothing to do with direction. It's just an amount, meaning it's a scalar. And that was the whole point, if you recall, back when we did this back in physics. You know, how much work was done? I pushed this box across the floor. That's nice. Does it matter which direction you push it across the floor? If it's a horizontal floor, it doesn't matter at all. It doesn't make any difference whether you went east, south, north, whatever. It doesn't make any difference. It's just a scalar. You did an amount of work. Right? The direction was not important. And that's a big deal. Okay. So you're like, oh, I see. Now I get like why I would do it, I guess, kind of. But all right, can you tell me how to find this dot product? I'd love to, friend. Suppose you had x1, y1, and then you're like, can you do it with z1 too, Jay, if you like? Sure, z1. Can you do it with w1 too, if you want to? Yes. So here's your two vectors. Literally, it is this easy, friend. x1, x2. Now that's straight multiplication. Plus y1, y2, plus z1, z2. And friend, that is just equal to a scalar. It's a number. It's 5. It's -3. It's whatever it happens to be. And kaboom! You're done. Wait, that's it? That's easy? That's it, man. That's it. Give me another example, or give me an example one. Love to. This is our vector A. I don't know why I wrote it on this side, but whatever. I'm just going to roll with it. Whatever. So let's find A dot B just for a good time, shall we? Okay. It's going to be -6 plus a goose egg minus 28 is equal to -34. Bam, done. Bob's your uncle. Piece of cake. That's it. Literally, that's it. Now, what I'd use that for most likely is to find the angle between these two vectors. Now, remember, it is important that they start from the same location. Now, we did this in 3D calc plot the other day. We said that, you know, it mattered. You had to tell it where to start from. So, in other words, you could picture them as starting from any location, but let's just say they start from the origin. It wouldn't make any difference. There will be this. There will be this idea that they are butt to butt, if you will, tail to tail. Okay, and it's that idea that when you put them tail to tail or butt to butt like that, okay, then we're trying to find the angle between them. Okay, now a couple of things strike me here. Obviously, the biggest angle you have between them is 180. Obviously, okay. I mean that goes without saying, because as soon as I get out here to 180. Right? If I go any more, you're like, oh, it's 181. No, it's not, you ding dong. It's 179. See, you're always going to go on the smaller of the two sides, which then begs the question. You're like, the cosine of theta is equal to A dot B over magnitude A times magnitude B. Of course, that bottom is a scalar as well, because those are just magnitudes. It's how long they are. But remember, what you're going to end up doing is taking the inverse cosine of theta. Right? That's what you're inverse cosine of, I should say, of this thing in a minute. And you're going to be finding theta. Well, inverse cosine, you may recall, is defined between 0 and 180. Okay? The inverse cosine will always fall somewhere between this. Okay? Always. And so that is part of the, the stuff you learned back in pre-cal, maybe somewhere along the line, math 112, whatever. And you're like, oh, yeah, I remember that. And then you've forgotten it, of course. And that's fine. But you just be aware of that. Okay? So just kind of picture that in your head. Obviously, if what's going to control the sign of this guy is this. If A dot B is negative, okay, we're going to be somewhere between 90 and 180, right? Because, clearly, that would give us the negative cosine is going to give us in the second quadrant. Right, and of course, at the bottom is you're multiplying lengths, so length times length always going to be positive. But on the top, that's where you can get the negative or positive. If it's positive, of course, you're in the first quadrant, which of course then begs the question: what if it's 0, Jay? Oh, good question. What angle has a cosine of 0 that we know and are love and happens to fall between 0 and 180? 90. Okay, and so that's going to be kind of a big deal. So in this case, I'm going to find the cosine of theta. It'll be negative 34 over. Now, what's the magnitude of this dude? I don't know. It's too much work. Let me get my calculator out. Excuse me. Goodness. Mercy. It's going to be 9 plus 16 plus 49. So, square root of 74. I'm just going to go ahead and write that right there. Nice. Times 16 and 4 is square root of 20. Bam. So, what I'm going to do is I'm going to come here. I'm going to go inverse cosine. Make sure you're in degrees when you do this, please. Is it wrong to do it in radians? No, you look weird, and it makes me gradient a little harder to do. Okay. So a couple things you can do. You can include a parentheses if you like, and multiply 2 square roots. But remember, when you take a square root times a square root, it ends up just being everything is inside of the square root. In other words, it's the square root of 74 times 20. And so we're going to get here that it's 152 degrees. 152 degrees. That is the angle between them. Okay. Let's do another. Let's say you have A is equal to 2, negative 1, 5, and B is equal to 3, 6, 1. Cool. Let's find the angle between them. Okay, cool, whatever. So I'm just going to go ahead and lay it out the way I've been doing it. Cosine. What are you doing? Cosine of theta. What are you doing? Is equal to Judas Priest. Let's take the A dot B. So it's going to be 6 minus 6 plus 5 over. And then the magnitude of A is going to be 25, 26, and 4 is the square root of 30. And then here you're going to have 36 and 9 is 45, 46. And so bring up the computer here and give it the old inverse cosine routine of 5 divided by, now, hey, it's 5. That means we're going to be in the first quadrant. By the way, 5 divided by a fairly good-sized number. What's that going to do to me, Jay? Well, I'll tell you what it's going to do to me. It's going to give me a very small trig ratio. In other words, it's going to be the cosine of a number, something like, I don't know, 0.2, 0.3, I don't know, very small. What's that going to do to me? Well, positive, so it's in the first quadrant. 0 would be 90 degrees. So we're going to be closer to 90 than we are to 0 in this case. In other words, if this came out to be awfully close to 1, if the numerator and denominator are almost the same, that'd be basically, if it was 1, if it came out to be 1, what that's saying is that those two vectors are going the exact same direction. Okay? If it came out to be negative 1, that means they're going completely 180 degrees opposite of one another. Okay, and we'll take a look at that in a jiffy here. Let's do this. The square root of, oops. There you go, dummy. 82 degrees. It's like I know what I'm talking about once in a while. How about that? Nice. Okay. And I'm not going to fiddle-faddle with the decimals right now. I don't care that much. Obviously, a couple decimal places is cool. Don't get carried away for what we're doing right this second. We're just experimenting. Now, let's do this one here. Nice. Let's do these guys. Cool. So if you want to find the angle betwixt them, it would simply be, of course, that's going to be 6 minus 20 plus 14 over. Jay, did you use this on purpose? I did. It's going to be 16 and 9 is 25, and 4 is 29. And this is going to be 49 and 25 is 74, 78. But it doesn't really matter because the top is a goose egg. Over, I don't know, but it doesn't matter. Hey, what angle has a cosine of 0? 90. And this is a big deal. If A dot B equals 0, then A is orthogonal to B. That is a fact. That is always true. That is a big deal. And as I mentioned in statistics, we talk about that a lot. So we're going to actually talk about that a little bit more. You would talk about that a little bit more in a statistics class. Yuck, coffee's cold. Okay, so keep that in the back of your head. Okay, dot product equaling 0 means we have orthogonal vectors. That's a big deal. It is a huge deal. If it's not 0, hey, they're not orthogonal, friend. Okay, it's that easy. Not a problem. How about this guy here? You're like, Jay, this one's too easy. No, I know, but just go with me on it. They're going the same direction, Jay. I know. No, I know. I know. So what are you going to do? I don't know. Let's find out. So the cosine of theta is going to be, well, it's going to be 2 plus 2 plus 2, which is 6, I guess. Yep. On the bottom, you're going to have square root of 1. And then you're going to have the length of that guy is going to be 2 squared is, wait, not square root of 1, you idiot. The length of this guy is 1 plus 1 plus 1 is 3. Attaboy. Good night. And this one here is going to be, it's going to be 12. Or it's going to be 4 plus 4 plus 4 is 12. Attaboy. Judas Priest. And then, yeah, it's 12. Yeah, there you go. And then 3 times 12 is 36. And that is 1. Hey, what angle has a cosine of 1? Well, 0 does. Okay, what does that mean? That means that they are parallel. They're going the same direction. There is no angle between them. And obviously, if they're going opposite directions, what would that do for me? And what angle has a cosine of negative 1? 180 degrees. And it's that easy. It is that easy. Again, the big takeaway, the one thing you want to like highlight in the back of your mind somewhere, this baby right here. Okay, that is always going to be true. Always, always. Always, always. Okay? Now, I think it's kind of a cool, interesting thing we're going to do with this in a couple of days. We get into polar coordinate. We're going to, well, not polar coordinates, you dummy. Cylindrical and spherical coordinate systems. We're going to be looking at a couple of cool things, and we're going to come back to this dot product idea, and we're going to look at that. I'm going to have kind of a neat, interesting application of that when we get there. So it's kind of fun. Again, pretty straightforward kind of a deal. Not a huge problem. Now, I will say this: what would A dot A give you? In other words, if you have a vector that is something like, I don't know, let's just do one here, 5. This is A, cool. What would it do? What would happen if you did A dot itself? I don't know. Let's find out. So 3, 1, 5. That's a lie. I know what I'm talking about. And so you're going to get, let's see, what you're going to get 9 plus 1 plus 25, which is 26, 35, isn't it? Yeah, I think so. 35. What is that? Well, that's the magnitude of A squared. That's it. That's it. That's it. That's actually kind of a neat deal. Because if you want to do something, if you wanted to automate something, what you can actually do is have, like computer systems, if you want to find the magnitude of a vector, well, that's one way to do it, is to take the magnitude of A with itself. Or you find the magnitude of A, you take the dot product of A with itself. And then you're in good shape. It's kind of a neat deal. I'm going to show you this. I'm a firm believer in using technology when appropriate. I will require you do some of this by hand and show me the steps that you're doing. But it's kind of a neat thing that you can actually do on a calculator. Now, to put in a vector on one of these calculators, you're going to use the bracket symbol. So you're going to go like 2, 5, 9 or something. Bracket. And then the stow button, which is right above on. Stow. And then I'm just going to grab alpha A. Don't use X, Y, Z, or T. You will thank me later. You will be pissed if you do. You'll be so angry if you use one of those, because then later on you're trying to graph something, and you're like, I'm trying to graph something, and it says I have a matrix. Yeah, because you stored a matrix as your X value. And so you're trying to graph Y equals 2X plus 5. That's not going to do that. Don't do that. Stored is I like ABC. That's just me, but you do you. So I stored it. Now that's matrix A. That's a matrix A. It's also a vector. Okay, whatever. Now, a couple of things I can do with that is go math. Now, matrix, number 4 there. Now, I can do a couple of things with it if I want to. If I wanted it, instead of being a row vector, I could do a column vector. So I could just do like this. Oops. So I could just go alpha A transpose. I'm probably not going to do that, but I could. I could do that if I wanted to. And then down here to matrix, that's just, that in linear algebra, that's kind of handy, but for what we're doing right now, it's not a big deal. If you come down here to vector ops, which is hiding down here, I forget where it's hiding. Come on, Jay, where are you at? Vector ops, there it is, had a bib. Now, if you're too lazy to make your own unit vector, you can actually do a unit vector of a, there it is, okay? I will require you do that by hand. For my tests and stuff, at least you have to be able to show all the work. So if I don't see any work, I'm not giving you points for that, friend. Sorry, not going to happen. Vector ops, and then here's the dot product of, now check it out, you can just go A, comma, not A equals, comma, oops, parentheses, alpha, comma, alpha A, like so, and you will get 110. Of course, that's the magnitude squared. So then, of course, the guy simply just square roots that. And yes, you can nest those if you like. Square root of 110. That's your magnitude. Kind of a neat deal. Kind of a nice little change of pace there. Okay, it's doable. You can do it a couple different ways. That's nice. Notice that if you did A dot B plus C, where these are all vectors, what does this look like? Well, this looks a lot like distributive property. That's because it is. Okay, that's because it is. And so, of course, you could use a distributive property. You're like, Jay, is A dot B the same as B dot A? And, of course, the answer is yes. Why is that? Because what is the dot product? It's multiplication and addition. What are they both? They're both commutative. So would it shock me that the dot product would also be commutative? Well, I hope not. It shouldn't shock me. That makes perfect sense. Of course, if you had a zero vector, I wonder what happens if I take this vector dot with anything. I feel like I'm going to get the zero vector again. Duh. Okay? Well, that is useless, but that is true. So you will see this in your book if you're like playing along. Why is that true? Because 0 times anything plus 0 times anything plus 0 times anything is 0, obviously. And then you're like, well, what if you had a constant, or not constant, a scalar rather, times A dotted with B? Because remember, this is a vector times a vector, so that's going to be a dot product. This is just straight multiplication. Would that be the same as taking the scalar times the dot product? And of course the answer is yes, of course it would be. Oops, not if that's not a scalar. Yeah, of course it's the same, okay? And would it be the same if you multiplied the scalar by C first? Of course it would, okay? Okay, of course that's the same. Now, those are just all the formulas. None of that's new. None of that should be shocking to you because it's just our normal algebra rules. I'll be right back. All right, I'm back. So, again, to sum that up, the dot product, pretty useful stuff. It obeys all the laws you thought it would have, that it would have done for us. But the dot product's always going to be about an angle. Always, 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 always about an angle. Okay, that's why it's used when in that work calculation, because it has to do with the cosine of the angle. So anytime you're thinking about an angle with two vectors, you're always going to be thinking about a dot product. Always. Take it to the bank. Now, I'm going to draw two vectors out. I'm drawing this so that they're butt to butt, if you will. And there's going to be an angle here. That's great. Now, for the purposes of what I'm doing, I'm just going to draw a sunshine up here. It's the one from Kellogg's, got his glasses on and everything. 2 scoops of raisins or whatever. All right. Now, that he's directly overhead. He's going to be directly casting a shadow down to here. So my question is simply this. Can I find the length of that shadow? Number one. Can I find that? I think so. And then number two, could you tell me the direction the shadow is going? And some people would say, well, it's going the same direction as A. I 100% agree with you. So let's think about that for a minute, but not right now. So let's think about this. This yellow line down here is called this yellow line that I have drawn here is what we call the projection, and we're talking about the projection of B onto A. Okay. Excuse me. And the way we're going to write that is two ways. First of all, we're going to write it thus as the projection. That's not a highlighted P. It's just a projection of, in this case, we're going to write it this way, B onto A. Whoever we're projecting it onto is going to be the one down the bottom. Okay? This is going to be a vector. It is going to be a vector that's in the same direction as A, obviously, because it's literally been projected onto A. And in reality, the only difference between A and the projection of B onto A is the magnitude. And so, wait, that sounds like it's going to have a unit vector of A, if you will, right? We're going to find the direction of A, but just it's a one unit vector. And then we're going to multiply it by the actual length of the yellow line. So the length of the yellow line, or the magnitude of it, is called the scalar projection. Of B onto A. And we write that like this. And, when I first started teaching this stuff, I was like, why is it written that way? It's the component of B that's in the direction of A. And this is going to be a scalar. Nice. And so what you're going to end up doing is this. To find a projection, the projection of B onto A, you're simply going to take the component, the scalar projection, which is just a scalar, and you're going to multiply it by the unit vector of A every single time. That's all there is to it. Okay? Now, to me, that's the easiest thing to do in the planet. And you're like, oh, it's not hard at all, Jay. I agree. So check this out. If you come back up here, if this was just right triangle trig, and we're just going to pretend that you don't see this friend, pretend he's not here right now. Could you find the length of this yellow line? Sure. I would just take this guy here. This yellow line would simply be equal to the magnitude of B, that's the hypotenuse, right, times the cosine of theta. That's exactly right. That's it. That's it. That's what the yellow line's length is. That's all there is to it. And you're like, wait, I feel like I know how to do that kind of, Jay, don't I? I think you do. So watch this. So we talked about this a few minutes ago. We said, well, the cosine of theta is equal to A dot B over the magnitude of A times the magnitude of B, correct? That's easy. And so you're like, well, yes, that's what I want. Now, hold up, because this is kind of exciting, because look what you have here. To get what I need to multiply by this guy over to here, correct? Is that true? Oops. Yeah, it is. Well, that's easy. Yeah. So this right here, by definition, is what we call the scalar projection of B onto A. That's it. That's all there is to it. This bit right here. Nothing to it. Now you're like, it's that easy. It's that easy, friend. So then, to get it in the same direction, you're telling me all I have to do is take this thing right here. All I have to do is take this guy here and multiply it by this guy. That's literally all I'm telling you, sir. Ma'am, good job. Good job. That's literally all I'm telling you. Well, that's totally easy. I concur. To me, this is the easiest way to learn it. Now, your book books always write it this way, which slightly annoys me. I get why they do it, and in practice, it makes sense. But it's just a little weird. Because it's not obvious as to why that is. Remember, this is all scalar right here. This is all scalar. And so you end up with just this bit right here, and which is reality is this. Some books write it this way, and they don't tell you where it comes from, and it really pisses a person off because you're like, what's going on here? But remember, the magnitude of a squared is just a dot a. Okay? So it's not hard. Again, I prefer to build it up from this standpoint because, again, from right triangle trigonometry, to find this yellow length is simply b, the magnitude of b, times the cosine of the angle. That's it. And so to get there, it's literally start with this guy right here, which is the definition of a dot product, and then do some algebra. Sweet. And so that's what we call this fella. And then again, to get to the actual vector, you just multiply it by the direction. This is the direction of A, because it's a unit vector. Nice. All right, so let's do one of these fellers as an example. Let's suppose you have that A is equal to, and by the way, you can change it up, shake it up. If you did A on to B, everywhere there's an A, you'd put a B, and everywhere there's a B, you'd put an A. It's not hard. I want to do C on to D, Jay. It's the same thing, dude. It's just the same thing. Don't worry about it. Don't get all weirded out about it. Cool. Because I feel like it. Cool. Hey, whatever, man. So to do this, again, I'm just going to start off with, and let's just go ahead and find the scalar projection, and let's do B on to A, because why not? Okay, so it's simply going to be equal to, and again, if you come down, where's our previous page here? Let's go back and look at it. Again, what we're going to be doing is A dot B over the magnitude of A. Let's do it. So A dot B is going to be 14 plus 3 minus 8 over the magnitude of A, which is 66, I think. Square root of 66 should be. Is it? Now, can you simplify this in your calculator a little bit if you wanted to, Jay? Sure. Check it out. So I simply just do this, 7, 1, 4, and then stow. No, don't stow yet. Don't do that yet. Stow as A, just right over the last one, and then do it again. And this time put in your 2, 3, negative 2. Oops, wrong way, stupid. Try again. That babe. No, stop it. Now stow at, you hippie. Stow as B. There you go. Nice. So then when you do this, you can just come in here and go second math, matrix, sweet, vector ops, dot product, and then you can just literally go A, B. And you will get that it's 9, which is what I got. Nice, good for me. Nice. And then you could also do A dot A to find the magnitude of A. It should be 66. Let's see if that's true or not. See if Jay can do math. Hey, look at that! I can do math. What do you know about that? So square root of 66 is just the magnitude. Remember, 66 would be the 66 would be the 66 would be the square of the magnitude. So then the vector projection is simply this. See, it's 9 over root 66. That's not hard. And then times 7 over root 66, 1 over root 66. Oh, how do you know? Because we found that the magnitude was 66, so we literally divide by, and the magnitude was the square root of 66, so we just literally multiply that through. And you're like, that's kind of gross. It is gross. So watch this. Watch me pull the square root of 66 out and get 9 over 66. Wait for it. Times 7, 1, 4. What? Yes. So how long is this vector? This vector is 9 over the square root of 66. Square root of 66 is 8-ish. So 9 over 8 is like 1 1/4. 1 1/8-ish. 1 1/8-ish. So this vector right here is a skosh. Well, both of them are just a skosh over 1 unit long. Okay. So person can do it this way. I'll probably show you a couple different ways to go about it. I guess I could just do this. I can just go A. So I can just go A times 9 divided by 66. And then I'm just going to go ahead and hit enter there. Boom. And there's my vector. See that? Nice. Now, what I'm going to do is pull up this baby here. And I'm going to add some vectors just for a good time. I'm going to add a vector. And my first vector is going to be, what were they? Oops, let's come back. I need my keyboard back on. There we go. So my first vector was 714. So let's go ahead and plug that baby in. And let's make that just some garish color so it stands out from a crowd. Let's make it big so I can keep my eye on it. Cool, done, whatever. Okay, there it goes. We're going to change our window momentarily. Let's don't get all hung up on that right now, though, okay? So let's put in another vector. And this one is, I don't remember, 2, 3, -2. And again, let's go with some goofy color, pink maybe, sure. Let's make it 4, swell, whatever, done. Great, awesome. Now, let's add a third vector. And that third vector is, whatever my calculator said here was 0.954, comma, 0.136, comma, 0.545. And let's make it look something different. Let's make it wetto, as my son would say when he was a child. Make it large so we can all see it. Dude, there it is. Where is it? Hey, it's right on the red one. Why is it on the red one, Jay? Well, because you projected the pink one down onto the red one. If that's not what it looks like, you screwed up. Nice. Nice. That's it. That's it. Now, what would happen if we did this one here? So I'm going to do one more of these guys. They're not hard to do. And we do actually use this vector projections and scalar projections. Again, another place it shows up is in statistics. It's kind of behind the scenes. So perhaps you've heard of when you're doing regression, technically that's kind of what you're doing. And then when you talk about standard deviation and variance, you're actually doing a projection onto the orthogonal. That's where the error piece comes in at. But again, this is kind of all behind the scenes stuff. But it's important to understand that there's a lot of uses for this. It's not just, hey, learn it, Jay. There you go. Done. Okay, I did it. Neat. I'm going to do this one here. Now, frequently what I'll do on these guys is I will make them fairly small numbers because, again, I like to show what I'm doing in the 3D calc plotter. And so I want you to be able to graph them and see them. So I don't want to have like ginormous numbers. Are you with me? So it's kind of a pain to have to go change that window and everything. I mean, it can be done, obviously, but I can show you a small number just as easy as anything else. So here we go. So again, if I want to do the projection of, I'm going to do them both here. Now this time, maybe this time I'm going to do, no, I'm just going to do beyond A. You guys can figure it out, flipping it the other way. And this guy, of course, you're going to do this bottom one first because, well, it just makes sense. And so what you're going to do is A dot B. It's going to be -6, -4, -10. Interesting. Over, so this is A dot B over the magnitude of A. Sweet. And this is equal to the component projection. Nice. And so the magnitude of A would be the square root of, that's 25 and 16 is 41. 40 squared of 45. Bam. Okay. Now, right off the bat, what did we know about this? Okay. Well, what we know about this is we know that our angle was greater than 90 degrees because our that's going to be -20 on top. I don't know why I did this down. I'm just going to leave it at this for now. -20 over the square root of 45. Okay, that's the component projection. That's this guy right here. But what I was trying to say about that is we know that means that our angle is greater than 90 degrees. Wait a minute. If I have vectors that are like this, and I put the sunshine up here, per your picture, Jay, it's going to be casting a shadow down here. That's right. That what? That what? Oh, check it out, bro. Here's A. Here's B. And you're projecting B on A. But A is not over here, Jay. Sure it is. Sure it is. You're going to go a negative distance in the A direction. So the A direction is this way, but you're going to go a negative direction in that regard. You may recall back in the day, and maybe you don't, I do. I remember it like it was yesterday. My junior high experience was troubling, to say the least, in a lot of ways. But Mrs. Stockton, wow, she was crazy. She literally, I met her probably when I was 10 or something, my mom used to babysit for their kids. And her husband taught my dad in high school, okay? But like he was his first year teaching, but he also taught me his second to last year teaching or something, right? And so I just assumed they were the same age, but I don't think they were. I think she was quite a bit younger than him, but she looked like she was way older than him. Anyway, she then taught me in junior high. She was mean. She looked like a witch. She literally looked like the stereotype witch that you see, minus the pointy hat most of the year, although she did wear it at Halloween. That's literally all she did was put a hat on, and then like, oh yeah, I see your costume, nice. I came back after going through high school, through college, came back, she was still working, and then like 10 years later she retired. I'm like, you've got to be kidding me. She was like 100. My mom's like, she wasn't that old, she was just white haired all the time. But anyways, I remember her screaming at us about, look, to find the area of this triangle, it's base times height. I'm like, okay, I'm down with the base. Where's the height? She's like, it's right here, obviously. And I'm like, yeah, that's not in the triangle. And she would scream it and holler at me, and I'm like, I don't get it. She's like, it's right here, you dummy. And I'm like, yeah, that's not part of the triangle. What do you can't just draw this. And I was kind of dumb, okay? But it's the same principle here. We're just going to be going a negative direction, right? A negative distance in the A direction. So to find this projection, you're literally going to do this times this. And I'm just going to write it like this. Well, wait, I'm doing a projection of B onto A. Sorry about that. 2, negative 4, 5. Divide by, I'm just going to divide by the square root of 45. And you're like, well, that's handy. Well, kind of. So in reality, it's going to be, again, pull it out front. That's the only place where I think it matters or where it's kind of neat. And then if you just do this, you just come in and go, all right, 20 divided by 45 is, oops, what are you doing? Clear. So negative 20 divided by 45. Now you can do this. Maybe it's quicker for you to just do it one way, but you can do this too if you like. There's your vector, right? So 0.888, negative 0.888, and then 1.777, and then negative 2.222. Nice. Sweet. There's your vector, friend. All right, well, let's graph this baby over here. So just come in here and get rid of them. And then go back to add a vector. And again, this is just for your benefit. I mean, if you don't want to graph them, don't graph them. Don't graph them on my account. I don't care. 2, negative 4, 5. I just like to know that I'm in the ballpark because it annoys me to turn in something that I have no clue whether I'm right or wrong. Okay. Boom, done. Okay. Oh, I didn't turn it to a nice color. Here we go. Purple. Sure. Great. And vector and negative 3, 1, negative 2. And again, pick out some disgusting color. Hit enter. Did it graph it yet? Apparently it didn't graph it yet. Hit enter. There you go. Cool. And you're like, it doesn't look like it's greater than one. That's great. It looks like, was it supposed to be greater than 90 or greater than 180? No, greater than 90. Yeah, greater than 90. Yeah, there you go. Cool. Nice. Now, let's see which one is which here. We're doing B onto A. B onto A. And A was the 2 one. So A is the purple. So it's going to be out here, sticking out from the purple one, kind of coming out that direction. Nice. So let's go ahead and stick that baby in, and you'll see. It's going to be sweet. First time someone ever sees that, I think it freaks a lot of people out. You're like, that can't be true, Jay. No, it is. It is. It is. Don't worry about it, man. Wait, was that right? No, it's negative. Negative, and then 1.77. And again, by the way, if this does not go in the right direction, hey, you screwed up. Go fix it. Go fix it, man. I don't know about you. It kind of makes me happy when I mess something up and then I can see what I did wrong. You're like, nice. Oh, there it is, friend. Check it out. Nice. Nice. That's it. That's all there is to that. Do not make it hard. Do not make it hard. And for the love of George, if it's me, I'm going to memorize it like that. That's how I'm going to memorize it. Knowing that I can write it like this or like this, I'm never going to write like that. Knowing that I can write it like this is handy, But it doesn't make sense where that comes from to me. This makes sense. That's it. That's section 9.3. You have a good time with that.